All right, hello everyone. Welcome to the exam one prep video slash homework two review video. Happy Thursday. Hopefully nobody showed up to class today. And hopefully everyone has already gotten a chance to look at the homework two problems. At least familiarize yourself a little bit with them before we dive into the solutions of these. So for homework two, first, if you're watching this video and have not watched lecture 7 that was already posted, please do that first. This was the recap from Tuesday's lecture. It was at 2-3. And we finished, I added on some items onto this. So we finished that slide deck. The important thing is this is where we introduced thermal coefficients and thermal stress. So there's a problem, last problem on the homework that includes this. So please watch this. Just pause this video. Just go rewatch that. It's on Canvas. You know where to find it. The other thing too, try to watch or at least try to these problems before watching this video. I mean, I know these problems are probably out there on the internet, floating around somewhere. You're just doing yourself a disservice if you try to, or if you just look at these and copy it over for your homework. You know, homeworks are a small percentage of your grade compared to the exam. So really take the time to like give it a good effort ahead of time, and then look at these solutions to see, one, if you are on the right track, or then two, see ways to simplify it and make your life easier conceptually for it. As a reminder, for homework to submit only 4 of these problems. So there's 10 of them, and use the rest for practicing. And then also on Thursday, by the time you're watching this, the exam one front page or the formula sheet will be posted on Canvas. So you can download that, review it. You do not need to print it out. I will print it out for you and bring it to the exam. It'll be the front page of the exam. But any formulas that you do not see on that, then it'd be good to try to remember, and especially some of the terminology and what the variables actually mean, especially all those Greek letters. All right, well, let's get started then. So problem 1 looks something like this. I'm going to read it. Part of the control linkage of an airplane consists of this rigid member CB and a flexible cable AB. And if the force is applied at the end, shown P, and it causes a rotation of 0.5 degrees, so very small, determine the normal strain in the cable. So this cable is going to be the AB. Now, the original cable is unstretched. Now, so what we see that's given to us right away, we see that we have some dimensions. They're all in millimeters, so we would expect the forces and the forces to be in kilonewtons if we had to calculate it. What we also see is that this original length here is not given, so we might have to do some trigonometry to find this out. We're also asked to determine what the normal strain is of the cable. So strain, whenever you have something to figure out, write the equation down. Remember that strain is unitless. It is a ratio of the deformations divided by the original length. So what I'm showing in this equation here is obviously we have the length of the new cable minus the length of the original cable, and that's equal to the deformation. And then we divide this by the length of the original cable, or length AB. So LAB is going to be this right here. Obviously, we are given the other ones, but we are not given that value. But we can assume that in the original unstretched condition that we have a right triangle. And if we have a right triangle, that means we can call up our good buddy hypotenuse and figure out what this value is. So a squared plus b squared equals c squared. We actually use this as engineers sometimes. I'm not going to show the math, but find this out. You can also see it's a 3-4-5 triangle if anybody remembers what that is. But in this case, the LAB, using hypotenuse and trigonometry, the original length is going to be 1,000 millimeters. So let's think about what it looks like in the stretched condition. So in the stretched condition, we know that the CB is a rigid member, so that length is not changing. So that length is still going to stay at AB. But at 800 millimeters. But what is going to change is this new length, though. So A is staying at the same spot, but essentially B is going to be moving and rotating along this axis. So our new triangle, or the new length that we would need to find, would look something like this. And this is that LAB new that we would need to find, this new length. Now, unfortunately, this isn't a right triangle, so we can't use hypotenuse anymore. But what we can do is find the displacement of this point, so the new y and the new x, to form this new triangle. So really, this is just looking at trigonometry in this case, because we know we need to find the length of the new cable when it's in this stretch condition, but we have to get a little creative on how to find this length. So the new triangle, to make this a right triangle, would need to find what this new y is and what this new x is. And we can find that by using SOHCAHTOA, our good buddy SOHCAHTOA. So we divide this into a smaller right triangle, and knowing that the cosine is the adjacent over the hypotenuse, so the cosine of the angle of 0.5 degrees, which is this angle here. Yeah, since this angle is at 0.5, yeah, that's correct, because it rotates there. Then our new y is going to be 799.96, so very small change. And our new x is only going to be pushed out 6.98 millimeters. So the new length, although it's very small changes in the y direction, that x direction still gives us 4 millimeters of new length. So we go from 1,000 to 1,004.17 millimeters. So plugging this back into our strain equation, strain here, we can calculate the normal axial strain. And if we do this math out, it's 0.00417. And remember, the units need to be in the denominator and the numerator, to be millimeters over millimeters. And that would be our answer for problem 1. Okay, problem 2. Don't know why it's blurry. I apologize for that. A little bit of a flashback from some statics problem. But now we're asked to determine it with some stress characteristics. So the rigid being shown there, the blurry one over there on the right, it's at a pin at C and a steel wire AB connecting it. Determine how much this wire AB stretches when the distributive load of 100 pounds per foot is acting on the beam shown in the direction. Use the following material properties for the wire. We have a diameter of 0.5 inches, assuming it's a whole diameter. And the Young's modulus, or the elastic modulus of steel, is 29,000 KSI. So what we need to know is, what we're caring about here is the steel wire AB, which is going to be this one right here. So for the steel wire, we're going to need how much it stretches when the load is applied. So what we're going to do is this load, distributed load, is going to cause an axial force in the wire. And then the way to think about that, this axial force is going to cause a strain in the wire. And then this strain, from that, we can calculate the deformation. This is kind of the order of operations here. So first, what we need to do is determine what that axial force in the wire is due to the load. So what we can do is find that internal normal force, or the axial force, in AB, and we're going to call this N subscript AB. It might be shown as F subscript AB or P subscript AB. Just know that it's a force in the AB blurry wire there. So the way we can do this is by taking a cut here in the wire and then looking at the statics internally, knowing that everything is going to be summation of equal to 0. Since we have a pin at this point, we know we have a reaction in the X and the Y direction. But if we take the moments about point C then we only have the vertical component of the axial force, NAB. So that's where that sine 30 is coming from. Sine is opposite over hypotenuse. So 30 degrees, that opposite is going to be the vertical component. That's acting 10 feet away from the point C. So it's right here, the blurry 10 feet. And then we have the resultant of the distributed load. So remember, the distributed load is 100 pounds per foot, and the total length of that beam is 10 feet. So 100 times 10, that's 1,000 pounds, and that's acting 5 feet away from point C. So 5 feet away from point C, because it's rectangular, we take it in the center, and that's where that's coming from here. Now we put a negative in that because that is causing a clockwise rotation, and we set the positive as counterclockwise. So this is all equal to 0, and we can see the only unknown here is our vertical component of NAB. Now we don't have a horizontal component of NAB because that would be acting in the line of C. So it'd be acting in the same point as C. So there's no distance offsetting of C, which means there's no moment. So we don't have to include that. The moment contributed due to the horizontal component of NAB is negative, or is 0. Okay, so when we solve this, we find that the NAB is equal to 1,000 pounds. So nice number here. So remember, wire stretchings, meaning that what we have to find, the wire stretching means it's a deformation. And a deformation means it's something measured or with units. Now you can go the old-fashioned way as they showed up here and find the load and then find the axial force and find go linear here. Or if you recall, we have an equation for deformation as long as we assume it's in the linear elastic zone. So given how we weren't given any yielding stress or anything, we're going to assume that it's in the linear elastic zone, which means we can use this equation for deformation. Now, in my other lectures, you may have seen, okay, well, wasn't this a P here? Like, shouldn't this be a P? It's the same thing. I'm just showing it as a normal force in this case. Just remember that this equation is force times length divided by Young's modulus times area. It doesn't matter if you put an N, an F, or a P, whatever the units are in there, it's the internal force. Or sorry, whatever the variable is, it's the internal force. All right, so what we found to solve this, we know that our NAB is 1,000 pounds, or 1 kip. We know the original length. Well, we calculate the original length based off of the fact that this is a right triangle. I'm just putting that in inches here. So 10 feet is 120 inches, and then the cosine of that to find the hypotenuse of that area. This is going to be 138.56 inches. The cross-sectional area of the wire, since the diameter is 0.5 inches, that means the radius is 0.25. The area of a circle is pi r squared, so that's where that equation is coming from. And then the Young's modulus, which is given to us, of 2,900 KSI. So these are all the things for it. We plug this in to ensure that our units all cross each other out. So we have everything in kips and inches and square inches. So that works out, and our final answer will be in in inches of 0.0243 inches. So that would be how much it stretches. Let's say in this case, if we needed to calculate the strain for whatever reason, what is the strain in there? If that was the case, then we would just take this deformation and divide it by the original length that we found before. Original length being here. Since they're both in inches, that will work out. That would be our strain if we needed to find that. All right, let's switch it up a little bit and read some or do some problems on some stress strain data or outputs. All right, so we have a cute little graph down here. It is a little bit simpler than your homework 1 stress strain graph. But nonetheless, we're told that it's from a test specimen having original diameter of 0.5 inches. So original diameter, that means it's a circle, 0.5 inches. Cool, we got that. An original length of 2 inches. And if the specimen is loaded until a stress of 70 KSI, what would be the approximate amount of elastic recovery as well as the increase in gauge length after it's unloaded? Gauge length just means length of the specimen. So what would be the L nu? And then elastic recovery, remember, this is how much it bounces back once we go past yielding. So remember that for any stress that is greater than the yielding stress, this will result in permanent deformation. Now, the yielding stress from this graph, I wasn't told, but what we would do is we would assume the yielding stress is going to be right here. That should be specified, that will be specified in your exam, but this would be what we say the yielding stress is right here at about 58 or so. Oh, never mind, it did say it here. My bad. Yield stress of the material is 58 KSI. So we don't have to use the 0.2% offset method or anything like that. We're given explicitly what the yielding stress is. So elastic recovery follows the Young's modulus back to a stress of 0. So if this stress, if we load the material greater than 58 KSI, then the path back to a stress of 0 will follow the Young's modulus slope. And I'll show that here in a second. So remember that the Young's modulus, it's the slope of the linear elastic region, which means it's this right here. So this is something we're going to have to calculate in order to find it correctly. So let's go ahead and do that. Slope of this region, nice, easy, rise over run 2 points, 0.00 works. So 58 KSI divided by 0.002 inches over inch. That means our Young's modulus is about 29,000 KSI. So, I mean, right here, kind of cool. If you didn't know what the material was and you were just testing it, you could look back, and you've seen in the previous examples that we've done, this is about the KSI or the Young's modulus of steel. So right then and there, we kind of know it's okay, this is kind of close to steel. So for the elastic recovery, we are told that we load it up to 70 KSI, which is shown there on the purple line here. So remember, if you have a problem like this, make sure you understand that the y-axis is the stress and the x-axis is the corresponding strain, which leads to deformation. So the 70 KSI right here, if we were to unload and remove the stress, once we load to 70 KSI, what it would do is follow back using this green line, which is the Young's modulus. So the thing that it's asking for is the elastic recovery. Now, the elastic recovery is going to be how much the strain bounces back to. So this is the recovery strain, and this is the permanent deformation. So essentially, the recovery, think about this as how much the material snaps back. Now, since we went past the yielding point, will be permanent deformation, and that can be calculated by the permanent strain right there, shown at this point green. But we're asked to find the elastic recovery. So what we would do for this is we know that when it's loaded, the strain when it's loaded is 0.047. We get that by reading down here. And then we unload the material, and it's going to snap back following the Young's modulus back to this point, which lands at about 0.023 of strain. So the elastic recovery, or the recovery of the strain, is about 0.0024. Now, what we need to find with the recovery is actually a length. So how much is it snapping back? So this means we actually need units. If we need units, we need to transform this equation back to find that deformation. So the recovery in deformation, or in units, since the original length was 2 inches, we just multiply it by the strain to get our recovery. Super small number, 4.8 times 10 to the negative, or to the 3. Is that 3? I think that should be to the negative 3. Not bad. Should be to the negative 3 inches. Now, the permanent strain, let's say if it was asking for this, what is the permanent strain? Or yeah, it is asking as well as the increase in length of everything. So in this case, it's asking as the increase in length of the gauge length. So what is this L new? L new, the new length would be the original length plus the deformation. This permanent deformation is going to be the strain of 0.023. So the permanent strain is that. The permanent deformation, again, small number. I'm sorry, that should have been to the negative 3 there, but it'd be 0.023 times the original length, since that's the permanent. Now, it just so happens that the elastic recovery is similar to the permanent strain value of 0.0024 and 0.0023. This is just a coincidence of the problem. That's not always the case. All right, another stress strain diagram. So it's shown below. The yielding stress was determined to be 58 KSI, which is going to be right about here. So similar to before. So 58 sigma Y. And it ruptures at 85 KSI. So right here, that must be that failure point. We're asked to see what is the material's modulus of resilience and the modulus of toughness. So there's two things here. We're asked for the modulus of resilience and the modulus of toughness. Now, for the modulus of resilience, this is the energy required to reach the yielding stress of the material. So another way to think about it is like it's the energy required to push it out of the linear elastic range. So that yielding stress represents the linear elastic range maximum stress. So what would be the energy required to reach that yield stress? I remember we said that the toughness is the energy that will be required for the material to fail, so to reach the rupture point. Now, remember that for stress and strain, the energy can be calculated by the area under the stress strain curve. Now, this is a different type of like actual energy. This is the energy normalized by volume, but still in this case, this is still the values that we would use for modulus resilience or modulus toughness, at least for the purpose of this class. So for the modulus of resilience, the equation I showed you was this one, which is the yielding stress squared divided by 2 times the Young's modulus. But really, remember what it physically represents here. It physically represents the area under this curve right here. And it's a triangle because this is a linear elastic region. So really, can be derived by just a triangle, 1/2 times base times height. And that's where that equation comes from. So I wouldn't worry about memorizing this equation here. Instead, just remember that it's the triangle. It's an area under a triangle. So it's under the linear elastic region. The area of a triangle is 1/2 times the base times the height. We know that the base is going to be a strain on the x-axis, and we know that the height is going to be that yielding stress. So that's where that comes from here. So our modulus of resilience is 0.058, and modulus of toughness is going to be the entire area. So it is important. The toughness also includes the modulus of resilience inside of it. So when you're doing these areas, make sure you also include that area, that initial triangle. Now, in this case, this graph is a little easy, or maybe not easy, but it's not as hard as it could be, where we have these two additional areas, and these are just trapezoids. So you have to remember how to find the area of a trapezoid. The entire area under the curve, which is the modulus of resilience, plus this area 1, plus this area 2. So we look for the points on the x-axis. The area of the trapezoid is the A plus B divided by 2 times H, or the height of it. And of course, we have to turn it around a little bit because you can follow the math there if you're not familiar. But that's the area of each individual trapezoid. So the modulus of toughness should always be greater than the modulus of resilience, and it's 0.981 KSI. So the way you can kind of remember resilience, think about resilience as like the ability to like bounce back. You know, if you say somebody is resilient, or like maybe a coast is resilient, or like a lagoon, an environmental area is a resilient area, that means like whenever it is loaded, or whenever like you're hit with tough times, you're able to bounce back. So that should trigger the linear elastic remembering. And then toughness is like how much can you like withhold until you're actually break down. And so toughness is the energy for the final, like the max amount of energy before you break down, or before the rupture in this case. There's just some ways to remember the physical meaning between modulus, resilience, and toughness, instead of just trying to memorize the equation. Because for toughness there is no equation. It might be, this area beyond the yielding could look like this, it could look like that, it could just be flat, it could look like anything. There's a bunch of different types of stress and strain curves out there. So that's why there's no set equation for it. All right, done with some stress strain graphs. Let's look at a Poisson ratio example. So we're told that we have this plastic rod with an original length of 200 millimeters and an original diameter of 15 millimeters. If the axial load shown of 300 kilonewtons is applied to it, determine the change in its length and the change in its diameter. So the plastic has a Young's modulus of 2.7 gigapascals and the Poisson's ratio of 0.4. So right off the bat, if you have a problem like this, or anything, what I would recommend doing is remember what a gigapascal is. Like write that down. Giga, 10 to the 9, and a pascal is a Newton per square meter. The importance of that is because here you have units in millimeters, both kinds. So we would need to make sure to account for that when we're looking into an equation that includes the Young's modulus. So the Poisson's ratio is a function of the strains in the lateral and the axial direction. So let's think about what's happening if we're loading this with 300 newtons in both direction here. We would expect to see an increase in length in the axial direction, and then some type of contraction in the lateral direction. Now, the deformation, if we're just looking on one side of it, then we should expect to see half of the deformation, knowing that the other half would be here on this side, in the lateral side. So the Poisson's ratio is that ratio between the lateral and the axial deformation. And remember, that negative is just there to account for the difference in direction. When we have an object increasing in length in the lateral direction, it's going to compress in length in the axial direction, and vice versa. In this case, if we have a material increasing in length in the axial direction, then the strain in the lateral direction will be the opposite of that, or negative. So Poisson's ratio is always between 0 and 0.5. And it's good to recap and think about what those things actually mean for it, or like what the physical meaning of between those are. So Poisson's ratio is only valid in the in the linear elastic region. And the thing that we're going to be needing is the change in length and the change in its diameter. So we're going to need to determine the axial and the lateral deformation. And these are both derived from the strain. So we don't know any of the strains. We have what the loading conditions are, and we know the cross-sectional area, and we also know the Young's modulus. So we need to find this axial strain first. Now remember, axial strain can be related to normal stress through the Young's modulus. This is the slope of the stress strain curve. So if we're in the linear elastic region, then we're in that Young's modulus region, where we can use this slope, or this value of E, to estimate the strain if we have the stress, or vice versa. So since we can calculate the stress and we know the Young's modulus of 2.7 gigapascals, then we can set up an equation to solve for the axial stress. So we know that the axial strain. The axial stress is the force divided by the area. And so we can calculate the area here, and we know the force, 300 newtons. And then we divide this by the Young's modulus, which again is in gigapascals, 10 to the 9. And you can see then everything will cancel out here. where the newtons cancel out with the newtons, meters squared cancel out with the meters. Take note too that this is division, so that's a a fraction there, so they're not multiplying by each other. So our axial strain in units of meters over meters is going to be 0.00629. So from Poisson's ratio, so knowing this here, we can set up an equation to solve for the lateral strain. So we know that the lateral strain is just going to be negative 0.4 times the axial strain. So the lateral strain is going to be negative 0.00252. And again, the negative just means that it's contracting, it's not expanding. All right, so from strain, we need deformation since that's what it's asking for. The change in length, or the change in length is deformation. So the axial or the strain just in general would be the deformation divided by the original length. So our deformation is going to equal to the strain, since we know that, times our original length. So you just multiply this over and boom, that's how we get the equation shown there. So for the axial component, the original length is 200 millimeters, and the axial strain that we found here is 0.00626. And then for the lateral component, the diameter is 0.5 meters, and our lateral strain, 15 millimeters or 0.00515 millimeters, and our lateral strain is 0.00252. So we can solve for these, keep them in millimeters, and these would be our answers here for the change in its length. Remember, change in length, change in diameter. These are deformations. And deformations in our world are expressed by that little delta value there. So this would be the answer. All right, in this example, we're asked to find what the Poisson ratio is based off of the stress strain and the loading data given. So we're told that the elastic portion of the stress strain diagram for this aluminum alloy is shown down here in the figure. The specimen from which it was obtained has an original diameter of 12.7 millimeters and an original length of 50.8 millimeters. And when the applied load on the specimen is 50 kilonewtons, the diameter shrinks to that number with a bunch of digits, so I'm not going to read. So what we need to do is find the Poisson's ratio. And remember from the last solution, Poisson's ratio, shown by that nu, Greek letter nu, is the lateral strain divided by the axial strain. And also remember that strain is deformation divided by the total length. Or I should also say deformation divided by the initial diameter. In this case, the diameter would be a length. So what we need to find is the axial and then the diameter deformation. And so we know the axial deformation is the new length minus the original length. And the diameter deformation would be the new diameter minus the original diameter. So the new diameter, the lateral strain, the lateral deformation, we can find based off the information given to us. We're told that whenever the load of 50 kilonewtons is applied, we're going to have a deformation, the new diameter is 12.67494. So that means our lateral deformation is negative 0.02506. Now, the axial deformation we're not given. We know that the original length is 50.8 millimeters, but how can we find the new length? Well, the new length we can find from the stress strain itself. So we see that it's following this slope here of the Young's modulus. And we know that the stress on this y-axis is the internal force divided by the cross-sectional area. We're told that the internal force is 50 kilonewtons. So 50 kilonewtons or 50,000 newtons divided by the cross-sectional area. This is producing a stress of this crazy looking number. We're just going to simplify this to 394.7 megapascals. Now, why megapascals? Because that's what this is currently showing in. So we know that it would be somewhere around here. It's not to scale. You're not going to have to scale it. How can we find this point here, this strain? Now we could calculate the Young's modulus and solve for it that way. Or what you can see is that these are like triangles, right? They're both right triangles. And they both have the same little apex angle there. So from the larger triangle that we know of the y and the x component being 490 and 0.07, we know that it must have similar proportions to the y component of this smaller triangle of 394 and then this unknown strain here. So we can solve for that using like triangles of 0.00564 strain. Now we're not done yet. We still need to find the Poisson's ratio. So the Poisson's ratio, we found the lateral strain earlier. And now we just found the axial strain under our loading condition. And so our Poisson's ratio is about 0.35. Now note here that negative cancels out. So technically it's something like this, because this negative turns into a positive since we have a negative in our equation. So Poisson's ratio of 0.35. It's within that range of 0 to 0.5, so it should make sense, and then we're good to go. All right, a few more to go. Back in the statics realm, now we're going to be looking at some deformations applied with statics. So we have a triangular truss. It's made of 3 members, each from A36 steel, having a cross-sectional area of 0.75 inches squared and a Young's modulus of 29,000 KSI. Now, we see that at point C up here at the top, we apply some load P horizontally for some random reason. And what we want to do is to find the greatest load P or the maximum load P that can be applied so the roller support does not displace more than 0.03 inches. So when we talk about that, that means we don't want this roller to move this direction any more than 0.03 inches. So our free body diagram before we displace anything looks like this. Now, we are told that each segment is 16 feet long. So because each segment is 16 feet long, that means we know it's an equilateral triangle. And if we know it's an equilateral triangle, that means we know that each degrees is 60 degrees because 180 divided by 3 is 60. So that's how math works. So what we need to find is this deformed shape. We know that A is not going to deform. C is going to move down a little bit, and only B can deform in one direction, going to the right. So what we're going to first need to do is, or what we ultimately need to find is this displacement B, and then what will be the maximum P that will keep that within 0.03 diameter. So in this case, since everything is pin connections, A and B is really, or the segment AB is the only member deforming. So what we need to find is that axial force in NAB. So the deformation of this AB member from our previous is that it's going to be the internal force in AB times the length of AB divided by the cross-sectional area of AB times the Young's modulus of the material of AB. So what we need to do is find that internal normal force in AB, which I'm showing as N subscript AB. So let's do summation of moments at A equal to 0 to find our support reactions. So for the support reactions here, we need to find this distance away from P, that P is acting on it. And since this is a right triangle, we know that it's going to be 8 feet in the center, or sorry, an equilateral triangle, it's going to be 8 feet in the center. And then we can use Pythagorean to find this y component, right? A squared plus b squared equals c squared, knowing that this is 16 feet right here. So for moments, we go ahead around A. So we'll put our finger right here. And what are all the things that move it? So the BY is causing it to go in the negative direction at 16 feet away. And then the P is causing it to go in the negative or positive direction. No, also in the negative direction. Um, yeah, and also in the negative direction, 13.9 feet away. So by is can be set up as a function of p, since we don't know this p of 0.866 times p. Now let's look at the uh, like the section here at point B, so we can solve for NAB now that we know py as a function of b as of p. So summation of forces in the y direction equal to 0. Using the sign, the vertical component of the NCA. You know that NCA is going to be equal to, if you do this math out, it'll be like 0.99996. So we're just going to say it's equal to -1 times P, or negative P. And then the summation of forces in the x direction then would be that negative P cosine of 60, since we have the horizontal component, which is nice. It means it's the NAB internal force is going to be 0.5 times P. So what this means is, for every time we apply 1 unit of P, so if like P is equal to 10, the internal force at AB is going to be 5, or half of that. So now that we know, or at least have a function for NAB and function of P, we can solve this for NAB by rearranging this equation. And the reason why we do that is because we have a tolerance, or we know that this is going to be 0.03 inches. So NAB is equal to the deformation B, which is what we're saying is going to be 0.03 inches. That's the max. The cross-sectional area, which is 0.75 inches squared. And then the Young's modulus, which is 29,000 kips per square inch. And then we divide it by the length. Now, this is important. We don't put 16 feet here. What we do is we put this as 192 inches. And that is so all the inches will cancel out, and we will be left with kips only. So for NAB, since we know this is 0.5, this is equal to 3.4 kips, which means the maximum P that we can apply is 6.8 kip. So when we apply a load, a P at point C of 6.8, it will deform at B 0.03 inches. Maybe you'll need to design a triangle like this one day, and this will be helpful. But hopefully you can see the process of thinking of going from external forces to internal stresses to then determine the deformation requirements. All right, problem 8. This one looks familiar to you guys, so we're going to go through it quickly. Hopefully you already caught that. But now we have a different cross-sectional area, and hopefully you guys also realize that, spoiler, that doesn't really matter for this one. But let's still go through it. We have a steel hexagonal pipe, and a cross-sectional area is shown here. And it fits snugly between the fixed walls before it is loaded. So this is fixed on both sides. Let's determine the reaction at the walls when it's subject to the load shown. So we have this 2 times 8 kilonewton forces being applied at point B. Now we're going to assume the Young's modulus of the material is 50 ksi, or 50,000 ksi. And obviously we can't solve this because if we set up a free body diagram just using our knowledge in statics, you'll see we have one equation and 2 unknowns. So this needs compatibility with deformation to solve. So what we are assuming is we know that this 16 kilonewtons is going to want to deform if we were to remove one of the supports. So let's say we just remove the C section. So what we know is that this is going to want to compress at C in this deformation, this delta C. Now, this is the deformation from the external load. And then what we need to do is we need to offset this with an extension, or an equal and opposite extension from the support reaction. So we remove the external loading, And we say in the real world, though, there is a CX acting on it. And this is essentially pulling it in the opposite direction that it would have been deforming if it was free on that end. So this is the deformation due to the reaction force. We know that the deformation from C is going to be the force times the length that's deforming divided by E times A. And so from this, when we're on the free end, and we have these forces being applied here, which would be 16 kilonewtons, which of the sections would be deforming? That's what we talked about in class. This is the important thing. The only member that is stressed is this member AB. Essentially, this BC is just along for the ride. It's not deforming because the stress is not applied in that member. It's only applied in the A and B member. Now, if the arrows were pointing the other direction, then it would be it would still be the same case because, again, it's fixed on this side here and it's free on the other side in our make-believe make-believe superposition world. So if that's the case, this deformation C has the internal force PAB of AX and the length of the length is only the 300 millimeters. Now let's look at the deformation of the reaction force here. So we remove the external forces. What we have is that this CX is going to be applying this in the other direction, and that should have a deformation associated with it. Now, in this case, the entire length is being stressed. So we would use 1,000 millimeters. And again, think about the Play-Doh thing. I talk about Play-Doh a million times. This whole class should just be sponsored by Play-Doh if you're listening, anybody from Play-Doh. But really think about it that way. Like if you were holding one end of Play-Doh and you grabbed the other end and then pulled it to the side, the entire length of the Play-Doh would be deforming. If you grab the middle part of the Play-Doh and then pulled it, then only the part between your two fingers will be deforming. The other part is just chilling. It's just going along for it. So in this case, then the entire length, A to C, will be the length that we would use in our reaction force here. Now you might be thinking, okay, now we need to calculate the area since we have the Young's modulus. So how the heck do we calculate this area here for that? Well, let's set up the equation real quick. Since this is the same material, and since these deformations are equal to each other, what happens to these things here? They just cancel out. So although we have this gnarly looking area that I wouldn't even know how to solve, and since the Young's modulus is the same and it's the same area before and after, then these just cancel out and we can set up this very simple equation here. So keep an eye out for this. I think this was on like my PE exam. It's not, PE is completely different, but it was something crazy like this where the area just looked really like gnarly. You couldn't solve it, but really you didn't need to solve it. They just put it in here to try to like get you worked up or scared about the exam and think too much. So be confident in your answers when it comes like this. Like if you have something that looks too hard to solve, then maybe you don't need it. Remember the time constraints of the exam that you have. All right, so by doing this and knowing those ratios of length, we can solve for CX and then solve for AX by using this equation here. Once we know CX, we can find AX. And then boom, those are the support reactions and the answer for that. All right, 2 more to go, and these are doozies. So take a break. I'm talking to myself here. Well, let's knock these out. All right, so problem 9 here. The bracket is held to the wall using A36 steel bolts. So that's the type of grade of steel. It's at B, C, and D. Each bolt has a diameter of 0.5 inches and an unstretched length of 2 inches. Now, if a force of 800 pounds is placed 2 inches off, as you shown there, determine the force developed in each bolt. And for calculations, assume that the bolts carry no shear. Rather, the vertical force of 800 pounds is supported by the toe at point A right here. And all it's doing is causing a moment or a twist that would then want to pull these bolts out. We also assume that the wall and the brackets are rigid. So we're going to be drawing some triangles here, but really what we look at, even despite all this crazy looking geometry, what we're looking at is just an L bracket like this, a rigid member that's not going to deform. There's a support reaction here, in the A and the X, but it can rotate, so it's not a fixed moment. And then we have these forces, force B, bolt C, and bolt D. And these are acting these distances away, 0.5, 1.5, and 3.5. Now we know that this 800 is acting 2 inches away from the center. So in order to find FBC, FBD, and FD, we would need to set up the summation of moments around A. And we'll just say counterclockwise is positive, going to be equal to 0 here. Now we don't know FD, FC, and FB. So we're going to have to set this up based off of the moments here. And let's make this problem a little bit simpler by simplifying it like this. So this here is just going to be simplified into this equation. And obviously we have one equation and 3 unknowns here. So we're going to have to find something else to do. Now, let's push off this equation off to the side and think about the deformed shape, like that little graphic there. So remember, the L is staying completely the same, and it's rotating about here. So there's no deformation in the bracket itself. All the deformation is coming from the stretching of the bolts. So this is going to be equation 1. And we know that all of these bolts are going to deform. So we have the deformation of D, deformation of C, deformation of B. Now the key is this point here. Since this is the like point, this is the same angle, which again means if we think about these from a triangle perspective, all of these points are the same angle, which makes our life super easy because they're all just ratios of each other. So all we need to do is find the deformation of one, and we can set up these knowing that since they're all have the same apex point, the same light triangles here. So keep in mind there with this, if you're not familiar with like triangles, call your third grade math teacher and ask her to review it, or whenever we learn this in geometry. I guess I should have color coordinated those, but you can see that here how we're solving for that. That's where those values are coming from. So we're going to set up some equations with deformation, knowing that it's the axial force, which in this case now I'm just calling F for whatever reason, just got tired of putting N, times the length of the axial member, and then divided by the area times the Young's modulus. Now in this case, what we're looking at is of the bolts, since we know the bolts are the things deforming, and we're told what the initial length is, right? Initial length of 2 inches. We're also told that the force P is being applied here, and that's going to cause some force here. So these forces are the things that's also unknown, right? But wait a second, we actually have an equation for these forces here. So we have a lot of equations here, but now we have 2 more equations based off of these ratios here. So now we have 1 equation, 2 equations, 3 equations. We're starting to get more equations now, even though we're adding a few more unknowns. So what we do here, we know that there's a compatibility of displacements. So we can set up a system of equations here. Or we can rearrange these fractions just to put them in line so we can make them a little bit easier to work with. So let's do that here as a function of deformation of C. So again, knowing that the deformation, it just in general is FL, or the force times the length, divided by AE. For these A36 steel bolts, again, all of the same material, so we really don't even need all of those A's or the E's. You can plug that in if you want, but what you'll see is they all cancel out. What I'm doing here with these equations is just plugging this in here. Hopefully you can see that come from the point. Well, I guess, sorry, this should come down here. 0.223, 0.223, and then 0.33, 0.33. So the L's and the A's and the E's all cancel out because it's all the same material and they're all the same length. So this makes it a lot easier here. So we have now both the forces in the D bolt and the B bolt as a function of the C bolt. So now we can plug that all into our original equation and solve just for FC, so the C bolt. Show the math out there. We have a force in our C bolt in that middle one of 162.7 pounds. And once we have one, we plug that back in here. We plug that back in here, and we can find the force in the D and in the B. Boom. Isn't that cool? So, like triangles, compatibility, that allows us to solve some of these complex things, sprinkle in a little statics, and always look to see, what you can cancel out here. Same material, same diameter, then you do not need to calculate A and E if we're talking about a compatibility problem. Compatibility meaning, okay, if one thing deforms this amount, since it's attached to the other thing, then that thing must deform the same amount. Okay, last one. This is a thermal coefficient problem. And it is a assembly of three different types of materials with three different areas or cross sections. So they have different Young's modulus, different thermal coefficients. For whatever reason, they're on a fixed support shown in that little cartoon on the bottom. Now, what we want to do is determine the average normal stress in each material when the temperature reaches 110 degrees Fahrenheit. So at 70 degrees Fahrenheit, where it currently is, it fits snugly inside this area. So snugly meaning they're just kind of resting here perfectly. There's no stress developed. Now, as we heat it up to 110 degrees, we know these materials will expand. And so that will want to push against our support. And as soon as we create a support of dx and ax, then that's going to produce some type of internal stress applied. So we know that this is an indeterminate structure. We also know that the total deformation across the entire thing, since it's fixed, so from A to D, it's not going to expand at all. So that means that the expansion due to the change in temperature is going to be equal to any contraction due to the reaction loads. So that's where this superposition comes from. So what we need to do is we need to find the internal forces as a function of the reaction force. Choose one, AX or DX. And remember, there's no external loads, but the external load is a fire, I guess you could say, is the thermal expansion. So the deformation due to force is here. So this is due to force. The deformation due to temperature is here. And so what we know is that since these two will be equal to each other, since they are offsetting each other, as stated here, that the summation of all the internal forces will be equal to the summation of all the expansion of the temperature due to the temperature. So let's first look at the thermal expansion. So the change in temperature is going to be from 110 to 70, so 40 degrees Fahrenheit. So this crazy equation, we can bring that temperature on the outside here. So that's where this is coming from. So this is degrees Fahrenheit. You can see the alpha values are shown here. Place a close attention to each one of those and the units, or sorry, not the units, but the significant figures or the scientific notation, I should say. And then each one of these is the length. So this is 4 feet, 6 feet, and then 3 feet. So in this case, hopefully it's clear. This is aluminum or aluminum. This is bronze. And then this is our stainless steel. Not sure what type of structure this would be, but that's what the textbook cartoon is telling us. So we're going to roll with it. All right. So the thermal expansion. So what we would expect to see is that we would expect if this was able to expand and it was not attached to anything, then we would expect to see a thermal expansion, a total of 0.0055 feet, 55 feet. And now we know that it's not actually able to expand because it's fixed at A and D. And so we know that this thermal expansion or thermal deformation is going to be equal to the summation of all of the internal forces developed. So the deformation due to loading, again, just knock this over here just to keep it over here. Let's find what that deformation due to load is. So there's no external loads. So that means that this is all due to the reaction forces. So this N here is is the thing that we need to solve for, since we're asked to find the average normal stress in each material. And so we have it in inches total, and the summation of each one with the Young's modulus according to what we have here. So again, this is aluminum in this one. This is the bronze. And then this is the steel. And so you can see the diameters, sorry, the lengths are shown here. And then we have the diameters or the areas here. And so the total axial deformation, if this was able to expand or like that, sorry, the total axial deformation based off of the force is 1.3 times 10 to the negative 7. Let's put these in the same units. So instead of feet, they need to be comparative inches to inches. So we can solve for the normal force to be this large number, or 277 kilonewtons. Now, just to make sure that we're clear here, this is taken from setting this axial and then setting it equal to the thermal expansion, and then solve for N. All right, so we're not done yet because we need to find the average normal stress in each material. So we have the normal force. Or axial force, I've been calling it. So now we just need to divide it by the cross-sectional area of each. We'll go through this kind of quick. I showed the calculations for aluminum, but just make sure you change each one. So for the bronze, it'd be 16 pi. For steel, it'd be 4 pi. And these would be the answers. All right, go back and rewatch problem 10, because I know you probably spaced out during it because there's a lot of things there, but make sure that that's clear how we can use the thermal expansion as a compatibility equation with the internal stresses. All right, save this video. It might help for when you take the FE, review it at your pace. You guys know how to use YouTube. I'll put the little markers at the bottom so you can find each problem. Keep in mind, exam 1 will be on Tuesday, February 10th. It's in class, paper-based. You do not need to bring the formula sheet. I will print it out. And just generally with the exam, keep track of units. Remember that like stress is force divided by cross-sectional area. Make sure to cancel those out when you need to. If you can't think of an equation, then most of the time your units are going to help tell the story of how to actually solve for it. Always look to simplify a problem. Think about what you need to find, what your goal is, the solution, and how to get to it. There's going to be information that you might not need, just when you know that. So, don't try to squeeze all the information that you have that is given to you into an equation. Think about what you need, think about what you need to get there, and then just use what you need and make the assumptions you need to. I'll see you guys on Tuesday. Happy studying. Thank you.